All right, so chapter 5, vector calculus. A great many physical situations of interest to engineers can be described by calculus. I know this comes as a shock to many of you. It can describe how quantities continuously change over, say, time, and gives tools for computing other quantities. We assume familiarity with the fundamentals of calculus: limit, series, derivative, and integral. From these and a basic grasp of vectors, we will outline some of the highlights of vector calculus. Vector calculus is particularly useful for describing the physics of, for instance, the following: mechanics of particles, wherein is studied the motion of particles and the forcing causes thereof; rigid body mechanics, wherein is studied the motion, rotational and translational, and its forcing causes of bodies considered rigid or undeformable. So far we've gotten through your dynamics class, right? I mean, not that that's the end of rigid body mechanics. It goes well beyond that in detail, but that's where you guys mostly studied that. Solid mechanics, wherein is studied the motion and deformation and their forcing causes of continuous solid bodies, and by that we mean those that retain a specific resting shape. And then finally we're in fluid mechanics, wherein is studied the motion and its forcing causes of fluids, which include liquids, gases, and plasmas. These two together are sometimes called continuum mechanics. So you did a little bit of solid mechanics in your mechanics of materials course, and that is a subject that also goes very deep. And then you have a course on fluid mechanics as well, which is introductory as well. And then heat transfer, wherein is studied the movement of thermal energy through and among bodies. You guys had a course on that. Electromagnetism, wherein is studied the motion and its forcing causes of electrically charged particles. There are more, but this is a decent list. I will add to the list that any sort of lumped parameter, state space model. Can also be treated in this sort of vector calculus way, and there are a lot of really fun ways to analyze dynamic systems in this way. Dynamic system modeling is something that you guys have some exposure to through mechatronics, through system dynamics, and there are other examples. I would say it's also very useful when you have specifically nonlinear systems, considering your state vector to be a vector in Rn, and considering its trajectory, which is defined by the state equation, is useful. This last example of electromagnetism, so the one before the one I interpolated in there, was in fact very influential in the original development of both vector calculus and complex analysis. For an introduction to complex analysis, see the Kreisig Part D. I hopefully will have one lecture on complex analysis at least. It is not an exaggeration to say that the topics above comprise the majority of physical topics of interest in engineering. A good introduction to vector calculus is given by Kreisig in chapters 9 and 10, Perhaps the most famous and enjoyable treatment is given by Shea in the adorably titled Divgrad Curl and All That, which is fun. It is important to note that in much of what follows, we will describe typically the three-dimensional space of our lived experience as a Euclidean vector space, an n-dimensional vector space isomorphic to Rn. As we know from linear algebra, any vector v in Rn can be expressed in any number of bases. That is, the vector v is a basis-free object with multiple basis representations. The components and basis vectors of a vector change with basis changes, but the vector itself is invariant. A coordinate system is in fact just a basis. We are most familiar, of course, with Cartesian coordinates, which is the specific orthonormal basis for B, or basis B for Rn, where we have the x direction, the y direction. They're all orthonormal, meaning that they're all perpendicular to each other. Manifolds are spaces that appear locally as Rn, but can be globally rather different and can describe non-Euclidean geometry, wherein Euclidean geometry's parallel postulate is invalid. Like a curved space for which there are multiple lines that, so if you draw a line on a curved space, and you draw a point off that line. If it's a Euclidean space, there's one unique line that never intersects the first line through that point, and that's the one way of thinking of the parallel postulate in Euclidean geometry. If you have a curved space, though, you can have it so that there are an infinite number of lines that go through that point that never meet this other line, or every line that goes through that point is going to cross the other line. So those types of geometries, non-Euclidean geometries, can be described by manifolds. And if you want to do dynamics on manifolds, then you're looking at doing calculus on manifolds, and that's what differential geometry is all about, a subset of which we can consider our current study. So using differential geometry in a Euclidean Rn is totally, your standard way of looking at vector calculus. It's just important to know, and this is a sort of subset of differential geometry. It's important to note that if you go to curved spaces, manifolds in general, you can do differential geometry on them, and everything works out great. But it's a little bit different, and it's important to realize that that's out there. A motivation for further study of differential geometry is that it is very convenient when dealing with advanced applications of mechanics, such as rigid body mechanics of robots and vehicles. A very nice mathematical introduction is given by Jack Lee, and Bullough and Lewis give a compact presentation of the context in the context of robotics. So they do differential geometry applied to robotics, and that's really pretty nice. So if you want to do vehicle dynamics, like spacecraft dynamics and stuff, it gets pretty messy, and using manifolds and using differential geometry that describe the dynamics on those manifolds is pretty useful at that point. So just like a little bit of an idea of like this part of what we're trying to do here is give you sort of an idea of what's out there and where to dig deeper. So if you're going to get into very complex dynamic systems, especially vehicle dynamics, you're going to end up seeing a lot of stuff that is differential geometry, and it may or may not be intimidating, to see it. So if you want to dig deeper into those subjects, those two texts are pretty good places. That's where I learned about it mostly. Okay. Vector fields have several important properties of interest we'll explore in this chapter. Our goal is to gain an intuition of these properties and be able to perform basic calculation. We're not, so in your math course, you probably focused on calculation. You may have seen proofs of things. You may have also done a more mathematical course that was focused on proofs. Or you might have done a more engineering-oriented course, which tends to be more focused on calculation. I'm actually not really interested to show either of those things to you guys. What I'm more interested in is trying to get you to see where the applications are and what these objects mean in these different contexts and how we can use them more broadly. So that's kind of my goal here. The applications, as we saw, are so broad that it's difficult to say, okay, here's like one thing you can say about all of these different cases, but we'll do our best to kind of get an intuition for what these different things are, especially things like what kind of physical meanings can we give to things like surface integrals, what kind of physical meanings can we give to the differential operators like div, grad, and curl, and how do we transform among them? What are the sort of main ideas here? And that's kind of what we're going for. So, yeah. Great. I will say, yeah, that's all I have. If you want to get into the nitty-gritty details, though, of this topic, I would recommend checking out the Kreisig book is good for giving you a little bit of proof and giving you some of the ways to calculate stuff. So it's pretty like direct, like here's how to calculate stuff. Div, grad, curl, and all that by Shea is actually a really enjoyable read. He goes at it through electromagnetism, and he says, okay, here's the very basic physics, and this is actually where it developed from, so it's kind of a natural way to do it. So when he's talking about electric fields and describing their different properties, and it's a pretty nice introduction. And I follow it very, very vaguely. Okay, any questions? All right.